Hi, Professor.
Hi, Vanessa. How are you doing tonight?
I'm good. How are you?
I'm doing fine. How are you going getting through these Lewis dot structures? Where are you at in your lecture?
We're right here. I'm just starting this one.
You're just starting Lewis dot structures and VSEPR, or because I'm on Lewis dot structures. I haven't quite gotten to VSEPR yet.
I think we're on Vesper.
Okay.
I haven't seen Lewis dot structures
You
actually.
had to. You can't do VSEPR without doing Lewis dot structures.
Oh.
That's the first step.
Gotcha.
As a matter of fact, when I get to the slide a little later, you're going to see the first step is draw the Lewis structure.
He might put them all in one then.
Yeah, I'm going to do the best I can. Okay, Vanessa,
Okay, that's okay.
because this is a lot of information, and literally, I'm not saying I'm going to get out of here in a half an hour.
Okay,
Okay.
that's fine. I have a question from the last lab.
Okay, which help remind me, what was the last lab? PLC.
Yeah.
Thin chromatography.
The chromatography. In the post lab, I got the last question at the end wrong, which was what was the three unknowns?
In the post lab, or in the post lab, or in the results?
In the results, in the one you grade.
Okay.
Yeah, I got that one wrong too.
Let's see.
And
what's
I got all of them wrong except that one, and it brought my grade down to a 60 for that specific one.
Okay, that wasn't graded by me. That was automatically graded.
Okay.
Okay. And we will see what's going on. There may be a problem in it. Okay. All right. If you noticed the pictures that you got, the pictures that were displayed in the results section, I think it was questions 13, 11, 13, and something or other, where they showed the thin layer chromatography. Are you aware of what I'm talking about?
Sort of. Let me pull it up real quick.
Okay, Vanessa, you don't
Yes.
have to. If you don't mind, can I show your? It's being shared. Do you mind if I?
Yeah, no, you're fine.
Okay.
Yeah, you can share.
Okay. All right, we are. The questions the ones I was talking about was, do you remember this one? Vanessa?
I can't see what you're sharing.
Oh.
Sorry.
Nope. Can you see it now?
Uh-huh.
Okay. There were two different sets of data that were given to you. One of them had the solvent front going to 5, and what actually was given to you in the student data had the solvent front going to 10.
Okay.
All right. So what you're saying is that this one, correct, Vanessa?
Yeah.
All right. What I would say from this is the only one that I see that matches is the iron.
Oh, okay.
You see it goes up the same amount of distance and it's colored the same.
Yeah.
So that's what you were supposed to see was, okay, I have one dot. That's the only spot I see in the unknowns. And it seems to match iron because of the color and because how far it went up the plate. So that should have been checked. These three should not have. That's why you got as many off as you did.
Okay. I was confused because it was the result lab, so I thought we were supposed to put down what we got from ours.
You didn't do the lab, did you, Vanessa?
Yeah.
Wait, you couldn't have done the lab. You didn't physically do the laboratory, did you?
No, I didn't physically do the lab, but we had enough data to find the unknowns.
Yeah, well, okay.
That's what I did too. I found the unknowns in the actual lab and not
In
from
the
that
actual
screen.
lab, are we talking about, okay, to the video for the laboratory?
No, I used the information you gave in the student.
Crap.
Uh,
Okay, hold on a second.
and I think that's what Vanessa did as well, if I'm not
That's,
wrong.
no.
Yeah, that's what I did.
Do you see my problem though?
Yeah.
I'm living with this, okay? Okay, I see what you're saying. All right, so the answer should have been, let's see. Bismuth, from your perspective, bismuth, copper, and cobalt, right?
Yeah,
Is that what you're saying?
that's what I
Ladies
got.
and gentlemen, I'm sorry. I'm sorry to hold you back here for a second on tonight's. That's a legitimate gripe and I will correct it, okay?
Thank you.
Dylan, you said you had it as well, correct?
Yeah. Thank you.
Okay, anybody else that's in here now? So I can just go directly to you. Okay, good enough. I will correct it, Vanessa, and you'll be good from there, all right?
Okay, thank you so much.
Thank you for bringing it to my attention, Vanessa. Okay. All right, guys, we got lots to do tonight. Mainly because I haven't gotten through VSEPR yet. I'm just on the verge of getting through it. And excuse me, I haven't gotten through the lowest dots yet. And in addition to that, we have a whole new thing. So I've got to kind of like incorporate two lectures into one laboratory. Okay. And let me see. Is everybody seeing my screen?
No.
Not seeing my screen. Okay. Now?
Yeah.
All right.
Yep.
Okay. To do VSEPR, you need to be able to draw a Lewis dot structure. Now, these are the rules, guys, for doing Lewis dot structures. From the molecular formula, you write down the elements. Put the least electronegative in the center. You're going to add up all the valence electrons. You have to remember, if you have an ion, you got to account for it. If you have a negative ion, you have to add electrons. If you have a positive ion, you have to take ions away, take electrons away. Put 2 electrons between each of the elements. Those are the bonds. Subtract the number of bonding electrons you used from the original valence electrons. Fill the terminal atoms completely with pairs of electrons. Note that hydrogen is already full if it's bonded to something because it only needs 2 around it. Subtract all these terminal lone pair electrons from the remaining electrons. If you have anything left over, they go on the center atom. If the center atom doesn't have 8, take a lone pair from one of the terminals and put it between the terminal and that central atom. You've made a multiple bond. Last thing, check to make sure everything has 8 electrons, at least 8 electrons around it. So if I'm going to stop share here for a second. And we're going to be drawing stuff. Everybody see my whiteboard?
Yes.
Yes, sir.
In many respects, the my Hillsborough lab is much better than the lab you guys are doing. because it really involves a lot of Lewis dot structures. Okay. Vanessa,
Yes.
how many valence electrons does sulfur have?
Sulfur 4.
Your second guess? A number between 5 and 7?
6.
6. How about fluorine?
Fluorine has 6.
Yep,
Nope, 7. Sorry.
7. So if I do the math up, SF2 has 20 valence electrons. Okay. Jasmina. Jasmina? She hates talking.
Hi.
Hi. Okay. What's going to go in the center here?
Selenium, sulfur, sorry.
Sulfur. I'm going to put my 2 F's on either side. Then what am I going to do between the F's and the S's?
Pair them.
Put pairs of electrons. I have to bond them to make sure they are in my molecule. So I have to put electrons between them. I subtract 4 from my 20, I get 16. Where do my next electrons go?
Around the fluorines.
Fluorine has 2, needs 6 more. 2, 4, 6. So 2, 4, no, don't do that. Undo. Thank you. 2, 4, 6, 8, 10, 12. I have 4 left. Somebody, where do they go?
Around the
Uh,
sulfur.
Around the sulfur. Okay. All right, we're going to do another couple.
You wouldn't double bond it?
No, because I don't have to.
Okay.
This is
So
what I just
when
drew,
would you have-
Vanessa. Okay.
Yeah.
I don't
So,
double
sir,
bond
when-
it because my center atom has 8 electrons around it. Okay, Vanessa? Khalil, did you have a question? Khalil?
No, sir.
Okay.
No, sir.
Okay. Now, we'll go with that's my compound. Phosphorus tetrafluoride monoiodide. Okay. How many valence electrons does phosphorus have?
5.
Somebody other than Dylan. How many does fluorine have?
7.
7.
And iodine?
7.
So I have, if I add this all up, I have 40 valence electrons, right? Is that true?
Yes, sir.
Okay. Again, what's going to go in the center? What's the least
Phosphorus?
electronegative? Phosphorus. Going to go in the center. I'm going to put it over here. Okay. Now, look at the atomic dot structure for fluorine and iodine. How many? You've already said there's 7 electrons around it. So how many unpaired electrons are there around fluorine and iodine?
1.
1 unpaired, which means how many things can it bond with?
1.
Can only
Can
bond with
bond
1.
with one thing.
So therefore, if this whole thing is a molecule, then I have to put all 5 of them around my phosphorus. Does that make sense to you? Have
Yes,
to.
sir.
I'll explain why in a second. So I have just used up 10 of my electrons in my 5 bonds here. 1, 2, 3, 4, 5. So I have 30 left. Okay. Where are they going to go, guys?
Around the fluorine and iodine atoms.
Very good. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I'm good. Only there's one little problem here. Can anybody see what the problem is?
Phosphorus has more than 8.
Phosphorus has more than 8 electrons. Okay, now I need you to get out a periodic table right now. I need you to find a periodic table. And we're going to do just a tad of going back to quantum mechanics. All right. When the principal quantum number is 2, when we're talking about the second shell, L can only be 1 or 0. In other words, if I'm in the second shell, I can only have p or s orbitals. Am I saying anything that's lying to you yet?
No.
No,
All right. I get to the third shell. My orbitals, my L values can be 2, 1, or 0. I can have d, p, or s orbitals when I'm in the third shell. Does that make sense to you?
Yes.
So what happens when I'm in the third shell and below? I have d orbitals that I can incorporate in with my s and p. I can incorporate them into this and add more than 8 electrons. But I have to be in the third shell or below. I cannot do this with the row that begins lithium and ends in neon. I can't do it. Does this make sense to you?
I'm a little confused. What? I'm just a little unsure of basically everything you just said.
Okay.
Why can't
Khalil.
you?
Khalil,
Okay, so
go ahead.
Yes,
Go
sir.
ahead. Talk to me.
so phosphorus has more than 8 electrons.
It has 5 bonds, right, Khalil? This
Yes,
one,
sir.
this one, this one, this one, and this one. It has 5 bonds. Each bond has 2 electrons. Those electrons are shared. So in effect, phosphorus has 10 electrons around it.
Okay.
It is allowed, Khalil. It is allowed. As a matter of fact, it has to be, because I've got phosphorus and this is a molecule. Fluorine can only be bonded to one thing. Iodine can only be bonded to one thing. So for me to have this whole thing bonded to each other, phosphorus has to be in the middle and it has to have 5 bonds coming out, which means it has 10 electrons around it. It violates the octet rule.
Okay.
All right. Are we good with that, Khalil?
Yes, sir.
The reason we're allowed to do that is that if you look at phosphorus, phosphorus is the 15th element. It is in the third shell. Because the third shell has s, p, and d orbitals, those d orbitals are out there, whether they're being used or not, Khalil. It has s, p, and d orbitals. And because of that, we can use one of those d orbitals to allow phosphorus to bond with 5 things.
Okay.
Okay? You don't like
Yeah.
it, do you?
No, wait, I didn't think that phosphorus had d orbitals.
Yes, it does. It
It
has,
does? Okay.
every hydrogen has d orbitals. Okay? The orbitals exist, Khalil. The orbitals are out there. They're just not
Okay.
populated with electrons.
Okay.
Is that making a little sense, Khalil?
Yes, sir.
Okay, good. Because I'm about to blow your mind one more time. Okay, guys, I have this molecule. And sorry, guys, that have had me already today. I apologize, but there are only a few instances. BeH2 exists. It is a real molecule. Now, Be has 2 valence electrons. Hydrogen has 2 times 1. So there are 4 valence electrons. If I draw this with beryllium in the center, I take 1 bond to hydrogen. I do another bond to hydrogen. I've used up all my electrons. I have none left. Yet beryllium does not have 8 around it. Yes, it is possible to not put in 8 electrons and still have a valid Lewis dot structure. It is possible.
Could beryllium bond with more, or is it at its limit?
Well, could it bond with more?
Yes. Yes.
It could, Khalil, if the other thing was the one that donated both the protons to make the bond.
Okay.
All right. That does happen. That does happen. For example, nitrogen. If we draw nitrogens, and especially, well, I'm just going to draw ammonia. There are things, and these are called ligands. They're special kind of molecules in which the bond is made by one of the elements delivering both lone pairs. Okay?
Okay. Yes, sir.
All right. So I'm not, Khalil, I'll be honest with you. I don't know if beryllium does that or not, but I know other things do.
Okay.
And they are called ligands. Okay. Are we fairly good about Lewis dots? Do I need to, guys, you tell me. I'm prepared to be here until 10 o'clock at least. I'm here, I'm using this more or less as a training ground for you doing Lewis dots and VSEPR.
I think I have an understanding of.
Okay, I'm going to do one more. IBR5. We have 42 valence electrons. Okay. 5 times 7 for the bromine and 7 for the iodine. Everybody understand that? We good with the valence electrons?
Yes, sir.
So what am I going to put in the center?
The iodine, sir?
Iodine. Again, do all 5 bromines need to be around it?
Yes, sir.
So we're going to put them around. I got 5 things around my iodine. Minus 10, I got 32 left. What do I do with my next? How do I fill this up further? Where do the next electrons go?
Round the bromine, sir.
2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. I'm done. And yet I still have 2 more left. Where do those 2 go?
Next to the iodine, sir.
Next to the iodine. So now in this case, iodine has 2, 4, 6, 8, 10 plus the lone pair. Iodine has 12 around it. So iodine has managed to steal a second d orbital. Questions about Lewis dots here, guys?
No.
All right, so we're going to go on from there. We're going to get into VSEPR at this point. Okay, let me see where I'm going. And if I'm going into VSEPR, are you seeing my PowerPoint, guys?
Yes, sir.
All right, if I'm dealing with VSEPR, I got to come up with some vocabulary. The first thing I'm going to say is an electron cloud. Electron clouds are nothing more than densities of electrons. A single, double, or triple bond counts as one electron cloud. Each lone pair counts as a single electron cloud. Lone pairs are those that are not involved in bonding. Bonding electrons are those that are involved in bonding. Am I saying anything that sounds ridiculous so far?
No, no, sir.
All right, so when I am talking about electron domain geometry and I am talking about valence shell electron pair repulsion, electrons are negatively charged. They want to get as far apart from one another as is humanly possible. So if I have something with 2 atoms on the end, an atom in the center, I've got 2 electron densities. They want to be as far apart from one another. The way they get as far apart from one another is they are 180 degrees away from each other. That's as far as I can get them apart. If this one starts going this way, this is pushing it back again that way. The electron cloud that's here is pushing it back. If it starts to drift this way, this electron cloud is again pushing it back. They need to stay as far apart as possible. If I have 3 things around the center atom, well then 3 things still make a plane. 2 things make a line, 3 things make a plane. I can put my center atom in the center, oddly enough, and I can add 1 atom here or 1 electron cloud here, 1 electron cloud here, 1 electron cloud here. If they're equally apart from one another, they're 120 degrees because full circle is 360. If I have 3 bonds, that means each one is worth 120 degrees. When I get to 4 things, I'm beyond the plane. When I get to 4 things, they spread out in a shape that you're seeing where my arrow is right here. That is called a tetrahedron. I have 1 cloud here, 2, 3, 4. I've got 4 clouds. But now I can incorporate the 3rd dimension. So instead of having all 4 of them, sitting on a plane 90 degrees from one another, I can prop up one and let the other three kind of like dangle below. And so instead of having a bond angle of 90 degrees, I have a bond angle of 109.5. Bottom line, VSEPR dictates that the electrons are going to be as far apart from one another as humanly possible. Okay? In order to determine my electron domain geometry, remember, my electron geometry is incorporating everything. It's incorporating the lone pairs and the bonding atoms. My molecular geometry cannot see lone pair electrons, can't see electrons. It can see atoms, can't see electrons. So the geometry is going to be affected a little bit. The electron geometry dictates the rough shape of the molecule. If I have two electron clouds, they're going to want to get as far apart from one another. It's going to be linear. 3 electron clouds, one's going to be up, the other 2 are down. Again, equally spread apart. That shape is called a trigonal planar. If I get 4 things around the center atom, I have one of my electron clouds go straight up, the other 3 sit down. That shape is called a tetrahedron, and it looks like that. 5 things around, you have trigonal bipyramid. And I'll get in, excuse me, I'm sorry, I will get into that shape later. Same thing, 6 things around the center atom, you have an octahedron. We're only dealing with up to 6. There are no 7 or greater. So that was the electron geometry. That sets the basis for how we view the rest of the molecule. But if we're looking at the geometry, if we're looking at water, I can see the hydrogen, the oxygen, and the other hydrogen. I can't see the 2 electron pairs. Yet, the 2 electron pairs help to set the original tetrahedron geometry. So I had, if you can visualize this, I got 3 things sticking down, 1 atom sticking straight up, but I can't see this one and this one. All I can see is this shape. So I've gone from a tetrahedron electron geometry to what's called a bent molecular geometry. And when I have atoms, if I have atoms, I can, sorry, I need to get that out of there. When I have atoms, I can dictate a bond angle. If I have 2 atoms bonded to a center atom, that bond angle is going to be 180 degrees. 3 things, 120. If I have 4 things, that bond angle is going to be 109.5. Picture of a trigonal bipyramid. You have 3 atoms which are on a plane with one another, and it's like having a trigonal planar on this plane. Then we have 1 atom sticking up, 1 atom sticking down. The bond angle between the one sticking up and the plane are going to be 90 degrees. The bond angles within the plane are going to be 120 degrees. The last one, if I have an octahedron, 1 up, 1 down, 4 at the 4 corners, all the bond angles are 90 degrees. Okay, let's take a breath here. Am I on solid ground? Are you guys still with me?
Yes,
Can I
sir.
hear an amen?
Yep.
Not a yep, an amen. I'm
Amen.
more into this gospel thing. Are you with me?
Yes, sir.
Not yes, sir. You guys aren't playing the game. I don't want to play anymore. Seriously, are you doing okay with this?
Yes.
All right. Now, one of the books we used to use is called The Burge. It has this wonderful, wonderful chart that I stole. Okay. First of all, if all the electron clouds are linked to atoms, in other words, if all of the electron clouds are bonding electron clouds, then the electron domain geometry and the molecular geometry are the same. If I have 3 atoms bonded around a center atom, like in BF3, the borons in the center, the 3 fluorines are out here. Each one of them contains, each one of the points on my electron domain geometry has an atom attached to it. That means my electron domain geometry is trigonal planar and my molecular geometry is trigonal planar. But if I have a trigonal planar molecule and I replace one of the atoms with a lone pair, a couple of things happen. One of which is I can't see the upper part here. That's got electrons in it. All I can see is this atom, the white atom, going to the blue atom, going back to the white atom. The shape becomes bent. The other interesting thing about it is this electron pair is more powerful than the bonding pairs. There's more force exerted down onto the bonding pairs than the bonding pairs can exert back up. What happens is this bond angle gets shrunk. The bond angle is less than 120 degrees. So 3 things around, 3 electron clouds around the center atom, electron domain geometry, electron domain trigonal planar. If one of the things is a lone pair, I have a molecular geometry of bent. Okay. Now I get 4 things around the center atom. I get 4 clouds around the center atom. My chart dictates I'm in a tetrahedron, electron domain geometry. If I have carbon, if I have methane, which is CH4, carbons in the center, each one of these white atoms would be a hydrogen. So if each one of the white ones is a hydrogen, my molecular geometry is the same as my electron geometry, which is tetrahedron. If I take one of those hydrogens away, like for example, I have ammonia, N is in the center, the 3 bottom ones are hydrogens. The thing that's up on top, the electron cloud that's on top, is a lone pair. So I can't see this. The shape I do see is a trigonal pyramidal. And again, just like this one had the bond angle reduced, these bond angles are reduced from 109.5 to about 107. Now I can take that another step. Instead of just having 1 lone pair, I can make this 2 lone pairs. In this case, I still have 4 things around my center atom. two of them just happen to be lone pairs that I can't see. So if I have something like water, where I have a hydrogen, an oxygen, and another hydrogen, the other two sites are occupied by lone pairs. So again, I have something that looks like a bent molecule. Only this time I have two lone pairs up here. They push down with even bigger force. So the bond angle here is about 104.5, even less than ammonia's is. Are we doing pretty good here, guys?
Yes, sir.
All right. Now I get 5 things around my center atom, 5 electron clouds. My electron domain geometry is going to be trigonal bipyramid. If I take one of those things, which was an atom, and turn it into a lone pair, I can't see it anymore. And the one that preferentially gets taken is the one in the trigonal planar portion of the molecule. So I have a lone pair out here that I can't see. That makes my molecular shape seesaw. And it kind of makes sense if you kind of like use this as the lever and this goes down and these go down and up. Kind of looks like a seesaw if you have a very vivid imagination, which some chemists obviously were on LSD and they had it. If I take a second atom away from a trigonal bipyramid electron geometry, all that's left is the up and down atoms and the one that's shooting off to the side. So in this case, I'm going to have a T-shaped atom. Trigonal bipyramid, 2 lone pairs, T-shaped. If I have 3 lone pairs, those all go on the trigonal planar portion of the molecule, and my shape becomes linear. 3 more to go, guys. If I have 6 things around my center atom, my electron domain geometry is octahedral. If one of those things is a lone pair, I can't see it. What happens then is I have a 4-sided pyramid. So octahedral electron domain, 1 lone pair, my shape is going to be square pyramidal. If I have an octahedron electron domain, 2 of the things are lone pairs. They're going to pick up the bottom and the top, and my shape is going to be square planar. So draw the Lewis structure, and you're doing VSEPR to determine the molecular geometries. Draw the Lewis structure first. Determine the number of clouds around the center atom. Number of clouds will dictate the electron domain geometry. Then use the chart that I just showed you to determine the molecular geometry by considering only the positions of the atoms themselves. Questions?
No, sir.
Okay.
Oh.
Last subject I got to talk about before we're going to get into some examples. This is another theory that we're going to discover. Can anybody tell me what the bond angles are in P-shaped orbitals? Remember, we have an X, we have a Y, and we have a Z. What are these bond angles?
Wow.
X, Y, and Z
For-
planes. How far are X, Y, and Z planes away from one another?
For which ones, sir?
If I'm talking about a Cartesian plane in 3 dimensions, right, Khalil?
Yes, sir.
All right, let's just talk about a regular graph. You have an X and a Y axis, Khalil, right?
Yes, sir.
Okay. What is the angle between the X and the Y axis?
90 degrees.
If I take it out to a 3rd dimension and I put a Z right in the center, what would the bond angle be between the X and the Z?
90 degrees.
And between the Y and the Z, 90 degrees. I've just shown you through VSEPR, the bond angles are not 90 degrees, are they?
Yes, sir.
So we have to come
No.
up with a new theory. And I'm going to get to it in about next week. For those of you that are in my lecture, for those of you that are not, you've probably either gotten to it or you will be getting to it in the near future. The new theory is called hybridization. In order to understand that the p orbitals don't dictate 90 degrees for every bond angle, if we hybridize an s orbital with the 3 p's, the whole mixture of those together kind of like makes 4 balloons that are in the shape of a tetrahedron. If I mix just one s and one p, that makes a hybrid orbital that is linear. If I have 3 things around it, that is an sp2. That means that it is in a trigonal planar shape. So this was a new theory to try and help explain something else. Bottom line, for this laboratory, just access this chart. If you have 2 electron clouds, the shape is linear, your hybridization is going to be sp. 3 electron clouds, trigonal planar, hybridization sp2. 4 electron clouds, tetrahedron, hybridization sp3. 5 shaped trigonal bipyramidal, sp3d. 6 octahedral, sp3d2. Now here's another thing I want you to realize. 2 electron clouds, I have 1s, 1p, 2 orbitals that are hybridized. 3 electron clouds, an s and 2p, I have 3 orbitals hybridized. Same thing with tetrahedral, trigonal bipyramid, and octahedron. Okay,
Yes, sir.
let's do a few practices on this, okay? I'm gonna stop share for a second, go back to my whiteboard. Perfect example. Okay? Khalil, how many things are around my iodine?
Including the lone pair.
Including
6.
the lone pair.
6, sir.
6. All right, if I have 6 things around the center atom, what's my electronic geometry?
Octahedral, sir.
Octahedral. I'm just going to abbreviate it. So, are all 6 things occupied by atoms?
Yes, sir.
Are they? Isn't this a site, Khalil?
Oh, no. No.
I have one site that's in
only
a
5 of them
lone
are.
pair, correct?
Yes, sir. Only 5
So,
of them are.
so again, I'm going to have to go back and forth here. Share screen again. This. Okay, Khalil, do you see the screen here?
Yes, sir.
We said that with 6 things around it, it's octahedral. I now have 3 choices. If there's no lone pairs, it's the molecular shape's going to be octahedral. If there's 1 lone pair, my molecular shape's going to be square pyramidal. If there are 2, it's going to be square planar. How many lone pairs were around there?
1.
So my
it would
shape
be
is going to
square
be
pyramidal.
simple enough.
Yes, sir.
Okay, let's stop share. Stop share. Stop share. Thank you. See if I can get somebody else up here. Undo. Undo. Crap. Undo. All drawings. Okay. This is my Lewis drawing for SO2. Okay. How many things are around the center atom? Be careful when you answer. Ian. You out there, Ian?
Yes, sorry.
How many things are around the center atom?
4.
How many?
Oh,
4?
wait. 2 oxygens. So wait, no, would it be 4?
I'm
'cause the
asking
double-
how many electron clouds?
4.
Remember, Ian,
Oh, they count as
double,
1, so 3.
triple bonds count as 1. So how many things are around my sulfur?
3.
So what does that dictate the electronic geometry to be?
I'll be honest, I don't have that chart written down for the third for what it would be.
Okay. All right. Stop share. Share screen. How about that? Do you see that?
Yeah, triagonal planar.
Trigonal planar. Okay, that's the electronic geometry. Okay. Were all the things around the sulfur, were they all atoms?
Yes.
And were all the things around the sulfur atoms?
Yes.
What is this thing, Ian?
Oh, wait, no. No. That's a
So,
solo.
It has 1 lone pair, correct?
Correct.
So you've already figured out that the electron domain is trigonal pyramid. Now we're going to go to the molecular geometry part. My electron domain is trigonal pyramid. How many lone pairs do I have, Ian?
1.
What is my shape?
Wouldn't it just be bent?
Bent. Okay.
Okay.
All right. Stop share. New share. Whiteboard. You like my new toy, guys?
Oh yeah.
Dylan, draw me the Lewis dot structure.
All right, 1 second.
No, do it. Tell me what to do.
So place 3I.
Those are meant to be the same. Okay. I got my 3 eyes in there.
And because I has 7 valence electrons, you know that there's 21 valence electrons to use.
Plus
the 1 negative, so it'd be 22.
All right. I've used up 4 of them making the bonds. I got 18 left.
Place them around the terminal atoms first.
Thump, 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 thump. 2, 4, 6, 8, 10, 12. So where do these 6 go?
On the central atom.
So how many things are around the center atom? How many electron clouds?
5.
All right. Do you need me to go back to the slide with the electron cloud geometry? Let's do that, okay?
Thank
There are
you.
5 things around the 5 things around the center atom. What's my electron geometry?
Triagonal bipyramid.
Trigonal bipyramid, absolutely. So I'm going to go down to my other chart. And if I have 1 lone pair and a trigonal, stop that, stop it. If I have 1 pair in a trigonal bipyramid, I have seesaw shaped. What happens when I have 3 lone pairs in a trigonal bipyramid? What shape do I have?
Linear.
Linear. How are we doing, guys? Do you still want more examples? You
It's
talk
making
to me.
sense.
What's that?
It's making sense.
Okay, then good, good. More examples or not?
No, sir.
No more? All right. Yeah, it's been an hour. I'm kind of tired myself. This is the 3rd one of these I've had. Are you seeing my screen?
We're seeing the
Yeah.
whiteboard.
You're seeing the whiteboard? Thank you. Okay, stop share. All right. Now, has anybody looked through the laboratory for this?
Yeah.
How many structures are there, Dylan? Somewhere between 15 and 20? Dylan? You don't have to tell
Sorry,
me exactly. Somewhere around there?
Sorry, my Zoom page closed out. Yeah, probably on 15, 20.
All right. Each one of those has 5 questions associated with it. Be prepared, all right? This is going to be a long quiz. Okay? When you get to the results section, there's going to be a compound listed. Draw the Lewis dot structure for that compound. Then answer the series of questions. First question. How many lone pairs are there around the entire molecule? Guys, you have to be aware of the question that's being asked. Sometimes the professor will ask you how many lone pairs are around the central atom. In this case, it is around the entire molecule. So again, hopefully I still have that whiteboard up there.
Nope, now your PowerPoint's up.
I know. Hopefully it's still written. Okay, so if I am counting the lone pairs that are around this entire molecule, remember, they're saying lone pairs, not lone pair electrons, lone pairs. And a lone pair is anything that's not involved in bonding. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 lone pairs. Are we understanding how that question works?
Yep.
Yes, sir.
Okay, now I gotta get out of here and go back to where I was. Okay, that's the first question you'll be asked. Second one is going to be a little confusing. First question, identify the number of electron groups. In other words, it's the same thing as saying the number of electron clouds around the center atom. I just drew, or I'm sorry, Dylan just drew I3 minus. There were 3 lone pairs around the center iodine and 2 bonding. Therefore, the answer to that question would be 5. Second question, number of atoms bonded to the central atom. The center atom had 2 other iodines. So there are 2 in that instance. Third question, again, this is where I tell you it could be tricky. Number of non-bonding electron pairs attached to the center atom. The center atom had 3 lone pairs. Answer there would be 3. The fourth thing is general formula. The central atom is designated with the letter A. Each atom that's bonded to it has an X with the subscript. So in my example of I3, my general formula would be AX subscript 2. Then you designate the electron pairs with an E and a subscript. So my overall general formula for I3 minus would be AX subscript 2, E subscript 3. Follow the directions. I don't know whether they tell you to just put a space between each answer or put a comma. Follow those directions. Questions about the second question here? Again, if I have NCl3, NCl3 has 1 lone pair around the nitrogen. So the general formula would be AX3E. Third question, what is the electron group geometry and the hybridization? Use the 2 charts I put in this slideshow. One is the electron cloud geometry chart. It goes through 2, 3, 4, 5, and 6 electron clouds, what that shape should be. I have a second chart which dictates the hybridization. So figure it out there. These are multiple choice questions. Fourth question, what is the shape the atoms make? They're talking about the molecular geometry. They're talking about the shape after you take into account the lone pairs. Remember, if there are no lone pairs on the central atom, the electron cloud and the molecular geometries are the same. If there are lone pairs on the central atom, then use the chart labeled molecular geometries. Now, the last question, is the molecule polar? To be polar, a molecule needs 2 things. 1, to have polar bonds. In other words, there has to be a significant difference in the electronegativities. I believe the range is from 0.5 to 2.0. So if there's a difference in electronegativity, then you have a polar bond. The next thing to be polar, the entire molecule has to be asymmetrical. Has anybody ever heard of a quaint old middle-aged custom called drawing and quartering? Anybody ever heard of that?
Yes, sir.
Do you know what it is? The drawing is they take a sword and they make slits around the arms and around the legs. Then they attach each limb to a horse and yell, "Giddy up." How much does if the horses are of equal strength, how much does the torso move? Not at all, guys. It's like if you have a 150-pound man on one side of a tug of rope and a 150-pound man on the other, and they're pulling with the same force, the center of the rope is not going to move. On the other hand, if you have a 280-pound man and a 150-pound man, that rope's going to move, isn't it? So what you have to have is the molecule to be asymmetrical. If it is asymmetrical and if there's a polar bond somewhere within it, then the molecule is polar. All right, I'm here for your questions, guys. I know it's a lot. That was a lot of information. I couldn't figure out how to do it in any other fashion, though.
I have one question.
I'm here, Vanessa.
What would you like to see for a calculation page? Or is there a
No.
calculation page?
No
you want?
calculation. As a matter of fact, I don't even believe there's a notebook here. What it tells you to do is it wants you to, if you read the instructions, I believe it tells you to do the Lewis dots in your handout page and just take photographs of that and use that as your notebook for this day, okay? Vanessa?
Could you?
Got it.
Yeah, so just the chart.
Just the chart. Right, time out. That's my understanding right now. And I just looked at it briefly. Read what the Dropbox says, okay, Vanessa? And besides, has anybody noticed lately what your grades have been on the notebook?
100s.
If you turn in the notebook, you've been getting 100%. That's because I told you a while back, I just wanted you to do one good notebook. You all have demonstrated to drawing one good notebook. So at this point, it just remains for you to submit them. We have just 2 more to go. Or actually, have you submitted the chromatography one yet?
I have.
Okay.
I haven't, sir.
I don't know whether it's been dated or not.
I think
Any
it's
case-
closed.
I'm sorry, Vanessa?
I think it's closed.
No, the chromatography one doesn't close till the 15th.
Okay. I'll take your word on it. I've just been grading them haphazardly as I come across them. So Vanessa, don't worry about it, okay? Just submit something. Dylan, you had a question.
Yeah. Could you make sure to upload this PowerPoint to our my courses?
Okay. I'm going to stop share now, okay? And I'm in manage quizzes, course content. Okay. I'm sorry, I'm trying to look for, oh yeah, there it is. Okay. Dylan, just for you.
Thank you.
I'm doing this for nobody else, guys.
Sir, I had a question about the last lab that we did.
Okay,
The
if you can
chromatography
hold
one?
on, let me get this uploaded, okay?
Oh, okay, no problem.
Okay, boom, boom. Greg stuff. 2045L. Oh crap, I gotta. Okay. Dylan? You there,
Yep.
Dylan?
Yep.
It's under the, crap, that's not where I really wanted it.
I
Sorry.
see it in the mini lectures.
Yeah, but I'm moving it. Trying to move it. Yeah, I moved it. It's out of there now. It's the bottom. It's the last thing that's in there. Okay.
All right. Thank you.
All right. Any other questions?
Yes, sir. I had a question about the last lab that we did.
Okay. Does it have to do with the unknown?
Yes, sir.
Okay. You use the, Khalil, you use the student data, right?
Yes, sir.
And you came up with bismuth, cobalt, and copper, right?
Yes, sir.
God, am I good? My crystal ball is just clear right now, Khalil. What happened
Magic.
is Vanessa and Dylan brought it up earlier. All right, what they wanted you to do. Do you remember they had like those little drawings in the questions?
Yes, sir.
They wanted you to use the drawings to make the answers.
Oh, that's
Yeah, all right. So what they ended up doing was they gave you the data in the student data for labs, and they already gave you the information in the quiz. So some
Oh.
people used the quiz information, some people used the student data. So now I got to go back and regrade all those silly quizzes, okay? Yes, Khalil, I will make sure,
Sorry about that, sir.
I will make sure that it will get done, okay?
All right. Thank
Is
you,
that
sir.
it? That it,
That's the only
Khalil?
question I had. Yes, sir. That's the only question I had.
Fine as kind. Happy to accommodate you. The rest of you are kind of understanding what's going on with this stuff?
Yeah.
Good, I can breeze by this stuff during the next lecture. I'm kidding.
No laughs on that.
No laughs on that. All right. Guys, if that's it, if you don't have any other I'm here. If you have questions about this stuff, I'm here. Remember, my phone number is 727-202-7275. And don't be surprised if there's not a recording of Ding Dong, the Witch is Dead. I'm not veiling my enthusiasm over the getting rid of somebody. Anyway, if that's it, guys, I will see you next week. Next week is our last Zoom meeting. In 2 weeks, we have a lab final, I believe. No, that is a check-in with the announcements as to when the lab final is.
I forget. Is the final open note?
Yes,
All right.
as far as I'm concerned, Dylan. Just make sure you label everything your notebook.
Yep. I have sticky notes.
There we go. Anything else, guys?
No.
No,
Khalil?
no, sir.
Okay, I thought, yes, you're allowed to use the notebook, any notes you want in the final. Guys, if that's it, I'm going to bid you adieu.
Have a good night.
Bye.
Night.
Good
Thanks.
night. Have a
All right,
good
have a good
weekend,
evening.
guys.
Good night.